We are moving on to chapter 5, where we're going to talk about continuous random variables now. Chapter 4, we dealt with discrete random variables, where x took on specific values, and here we're going to now shift to continuous random variables. So just a little refresher of what we mean by a continuous variable. Same thing's going to apply to a continuous random variable, and that is a continuous random variable can take on any value in a range of values. And the other thing that we can use to think about a continuous random variable is that the values are measured rather than counted. And we saw with the binomial random variable a really specific way where we were using a discrete random variable to count. In binomial, we were counting successes and trials. Okay, so specifically a continuous random variable is going to be something that's a measurement, something that's not counted. So things like height, width, weight, time, things like that. Okay, continuous random variable probability distribution can be represented in the same ways that we represent a discrete one, a graph, a formula, or a table. And there's many named distributions that have a consistent relationship, all right, between the values of x and their probability. So again, just like discrete random variables. So let's look at some of the properties of a continuous random variable probability density function. For some reason, when we switch to continuous, we replace distribution with density. It's not super important. Fortunately, it still keeps PDF as our abbreviation. We just want to recognize that what that means is a PDF is something that's associating values of x, the random variable, with their probabilities. So that's really the important thing to remember for the purposes of what we're doing in this class. So let's start off looking at the graph of continuous random variable PDFs. It's a curve or a smoothed histogram where we don't have individual rectangles, but we have a continuous line or curve that represents the PDF. So I have some examples here. This first one, which looks like a rectangle, represents a uniform random variables PDF. And that's one of the named continuous random variables. And the middle one is exponential. Again, another one of the named random variables. And then that last one there is normal. Okay, the ones that are in blue are ones that we're going to look at in this class. Things to know about the graph is that the values that the random variable x can take on or equal are along the horizontal axis, and you can see that they're all labeled as such. All right, we got x showing up, labeling that horizontal axis. Okay, now the formula that goes along with the continuous PDF is denoted as f of x. So if you can remember from algebra, this is function notation. And the values that the formula takes on for a given value of x are what are on the vertical axis. So those aren't labeled, so we can just go ahead and label. So the values that are along the vertical are these values, f of x. Okay, we're going to come back to some more probabilities, some more properties of continuous random variables, but first we're going to look at some more specific examples. Okay, first let's look at exponential. Like, what kind of thing might we expect in real life to have this distribution that we call exponential. If we let x be the amount of time in minutes that a postal clerk spends with his or her customer, it could be represented with this exponential distribution. So I'm just giving you a specific example of a PDF graph, a curve. It has that exponential shape, and you can see that it's got x along the horizontal. So it looks like values that x can equal are some anywhere from 0 to, at least 20. All right, and then the vertical is also labeled with the f of x values, the function values for each of those values of x. Okay, just for, informational purposes, here is the actual function that's used to find those function values associated with the values of x. So it's an exponential function. We are not actually going to be working with this function at all. We're not going to be working with any actual formulas or functions for continuous random variables. I guess I need to take that back. For uniform, we will, but it's not even, it's just a constant function. Okay, so that's exponential. Let's look at normal. If we let our random variable x equal a SAT score, we could represent it with this PDF graph and function. So again, we have the values of the SAT scores along the horizontal. All right, so it looks like x values are going from 500 up to about 2,500. Okay, so those are the values. X can be any value in that range. Values that this random variable x can equal. And along the vertical, it's not labeled, but there is implied that the values of f of x are represented. So just one thing to point out. So if we've got this value of x, let's say 1,100, if we go up to the curve right there and then over to this vertical, the value on the vertical is represented specifically by the function at that value of 1,100. So this isn't super critical to grasp, but if you can just relate this back to algebra, we're really talking about a function like we talk about in algebra or pre-calc. Okay, the other thing to notice and look at is this is the PDF function for a normal. And this is a generalized one. We actually are given what the mean and standard deviation are, and we could make those replacements for mu and sigma in there. But I mostly show this to you so that you can be happy that we're not going to work with it. We're going to let technology and tables do that work for us. But know that there is this underlying function that gives us these specific values on the density curve. Okay, let's look at a uniform distribution now. Suppose the value of a stock varies each day from $16 to $25 with a uniform distribution. Let x equal the value of a stock. So let's first look at what that means for the curve or the graph. The values that x takes on we're told go from $16 to $25. And the thing to know about a uniform distribution, that means that all values have equally likely probability. They're equally likely outcomes. That's what uniform means. So that means that from 16 to 25, the probability is, the function is constant. Okay, so the vertical, we have f of x, but we can actually figure out what that value is. It turns out that f of x for a uniform distribution is 1 over the largest value that x can be minus the smallest value. So in this case, that's 1/9. All right, so we can see that for every value that x takes on, the function value is 1/9. It's constant. Okay, so it only applies for when x is equal to 16 to 25. Okay, so that's the 3 quick examples. Now we're going to look at some more properties. Okay, probability for a continuous random variable is looked at differently than we looked at for the discrete random variables. The probability for a continuous random variable is going to be the area under the PDF curve. Okay, I guess it's not equal to f of x. So I'm just going to say that right there. That f of x is only giving us the curve, and we get probability by taking area under that curve. So if we think about area being probability, the total area under the curve, then if we think about total probability, that's going to be 1. Another property of a continuous random variable that is now different than what we have been looking at so far is that we always refer to probabilities of continuous random variables for intervals of x. So never just single values. So an example is if we have 2 values, and we'll just use, these placeholders a and b, and if we're looking for the probability that x is between those 2 values, okay, that's the kind of probability that we're going to look at. So for example, if we look at this uniform PDF, if we think about a and b here, we have got a is equal to 3, that smaller value, and b is equal to 6. And we can see that that shaded region, that area represents the probability that this random variable x is going to be between 3 and 6. All right, let's look at this other PDF. This is a normal. Okay, so we got x here, we got f of x here. And if we want to say, think about this value, let's call this value a. What if we want to find the probability that x is less than a? Well, that works because that's an interval of values. It's a and all values less than a. So this shaded area would represent that probability. Okay, we're not to the point where we can figure out what that is, but just conceptually, we want to think of the probability now as area. Okay, or we could say, let's say this is b, and let's say we want to think about the probability that x is greater than b. Well, that probability is going to be this shaded area right there. Okay, so yeah, notice we're not referring to f of x at all here. We are just looking at the area under the curve to identify those probabilities. Okay, if by chance you have studied some calculus along the way and an integral calculus, you might be thinking that, oh, this sounds familiar. And it's true. Finding area under a curve for most functions requires calculus. It requires taking the integral of a function, which is what this is. We are obviously not going to do that in this class. Calculus is not a prereq. We are going to use geometry and tables with probabilities and technologies for the probabilities of continuous random variables. Okay, I want to look at one more property of continuous random variable PDFs, and that is that the probability that a continuous random variable equals one single value is always, and this may be a mystery what this might be, it's actually always 0. Another way to say that is the probability that x equals a, some single value, that is equal to 0. And let's think about why that's the case, keeping in mind that probability is area. So if we've got this value a here that x takes on, so we got x is here and we've got f of x along along the vertical. Okay, so the probability that x equals a, all right, is going to be the area, okay, under the curve. All right, so if we think about area as being width times height, okay, now we can get the height part, okay? If we go up to that graph and go over to the vertical, that value for the height, right, is f of a. Okay, so if we're looking at the height of that line, that is f of a. Okay, so we can fill that in. We can fill in that height with f of a. All right, but what is the width of that area under the curve over a? Okay, well, the width we might think of getting as the difference between a and a, which of course is 0. So what we end up here with is this area is equal to width of 0 times some value, but anything times 0 is 0. All right, another way to think about that is that the area under a line actually, let me change that to be more specific. The width of a line is 0. Okay, and basically comes from what we did here, where we just said, well, if we want that width, we're going to take the difference between the beginning and the end, and the max and the min, and well, those are the same thing. They're a, so we end up with 0. Okay, so for continuous random variables, we're always going to be looking for probability for an interval of values, not ever a single value.